about galaxies, and I'm going to start by giving you kind of a star hopping guide to finding the Andromeda Galaxy in the evening sky at the moment. Okay, so on your screen you should be able to see my version of Stellarium, which is not realistic because there's no clouds in the sky. It's a nice clear sky, and to see the Andromeda Galaxy, we need to face kind of like east, northeast direction, okay? And of course it has to be dark, so I'm going to move time forward by 1 hour, 2 hours, 3 hours, okay? So this is around about 10:30 p.m. at the moment. So over the next few months, the Andromeda Galaxy will be rising earlier and earlier, okay? So we're kind of at the beginning of the season where you can begin to get good views of it. I'm going to switch the meteor showers off so they don't distract us. Right, okay, let's find out where it is. There we go. So it is there. Do you know where it is? Before I kind of jump to it, I don't know if you recognize anything on the screen at all right now, but there's two kind of ways to look for it by star hopping. I'm going to try and draw on my screen here so you can, let's see if this works. Okay, so I'm going to annotate, draw. Let's see if I can do this. So, right. So one of the kind of like easiest ways to look for it is to look for the constellation Cassiopeia. Okay, and it's a sort of W-shaped pattern that you can see high in the eastern sky as soon as it gets dark. Okay, so the W shape, if I try to draw it here, let's see if this works. Oh, pen switched off. That's worrying. Right, here we go. Of course it's black on a black sky. It would be, wouldn't it? Annotate. Let's change the color to something different. Let's change it to white. See if that works. So I'm going to try and draw. It's turning it. I can't do it. I can't do it. It's not going to let me annotate. That's really annoying. So what I'll do is I'll switch on the lines instead. Let's try that. Right, so there's a W shape up at the top there. That's Cassiopeia. Now, what you can do is you can kind of like find the middle of the constellation. I'm hoping you can see me little white mouse pointer on the screen. Can you nod? Nod? So, yeah, thanks. So if you find the kind of middle of the W and you trace out a curve down here, you kind of arc downwards, and the Andromeda Galaxy is right there. Okay, so I'll just zoom in so you can just check that it is the Andromeda Galaxy. Okay, so there we go. So you begin to see it there. Okay, so you find the W, you find that middle section here, and you kind of like just arc around to here. Now, if you've got a really dark sky, you'll be able to see this without too many problems. And the astronomer's trick is to use averted vision. That means don't look directly at it, look slightly off to the side, and you'll probably see it more easily. The other way you can find it is by using the square of Pegasus. This is not an obvious kind of shape if you've got any kind of light pollution around you, but there's a big kind of square of stars here, the square of Pegasus, and you kind of just like head off to the left till you find the next bright star, and then you go up and up again, and you'll hit the Andromeda Galaxy that way. So there's a couple of ways you can kind of like hop to it in the night sky. But if you're looking after about like 10 p.m. and certainly earlier and earlier over the rest of the autumn and winter, you shouldn't have any problems kind of spotting it for yourself. It is visible to the naked eye. The best view you'll get of it is not with the telescope. Okay, the best view you'll get of this is if you can get binoculars, in my opinion. Okay, if you look at the Andromeda Galaxy with the telescope, let me just put a little ocular on here so you can kind of see how it looks in terms of the field of view of a telescope. Okay, so what I've got here is how the Andromeda Galaxy would kind of look in terms of binoculars. Okay, maybe it won't be so colorful as that, but that's the rough size of it. Okay, if you were to point a telescope at that, so I'll try and change this to telescope, sweep through here, so various binoculars, there we go. So we're now kind of there. So that's sort of like the telescope view. And it doesn't look that bright through a telescope. Through a telescope, typically you get the core, which just looks like a big fuzzy blur. Okay. And because it's spread out over a bigger area, it doesn't look any brighter than it does through binoculars. So in my opinion, okay, it's usually the first galaxy people want to see through a telescope, but it's certainly not the most impressive through a telescope. So if you want to look at it, go for binoculars. If you've got binoculars on a tripod, or you can lean against something to hold them steady, that will give you the best views. Okay. Right, so there you go. So that's a brief guide to how to find it. Now, there are other galaxies in the sky at this time of the year. So look, here's a trick to finding the other big one. There's the Andromeda Galaxy. So you drop down, you've got a bright orange star called Mirach directly underneath it, and you just continue that line. And underneath it is the Triangulum Galaxy. So I'll zoom in a little bit so you can see it. This is it. So in the local universe, we're kind of like you've got the Milky Way, you've got the Andromeda Galaxy. These are the two big galaxies in the local group of galaxies. This is number 3. This is the Triangulum Galaxy. It's a little bit further away than the Andromeda Galaxy. It's visible with binoculars if you've got a really dark sky. This will look reasonably good through a telescope eyepiece. Okay, so it is worth chasing this one down. It's got lots of kind of like, it's popping with new stars. Basically, there's lots of gigantic versions of the Orion Nebula throughout this galaxy, and you can see some of the fuzzy blurs within the fuzzy blur of the galaxy as well, so that there's huge star-forming regions in here. I've definitely seen them like through an 8-inch telescope from Hawksley in the past. So there's a couple of galaxies to be getting on with. I should say both of these are on the Nastro Binocular 75 as well. So these are two of the easier targets on there. Right, okay, so stop sharing that. I will now share my presentation because I'm going to talk to you about galaxies this evening. So, you know what? Until kind of like 100 years ago, just over, nobody really knew what a galaxy was. So you've got people like Charles Messier who would find these fuzzy things in the night sky. And I've mentioned them lots and lots of times. Messier was interested in comets primarily. And every time he found one of these things that initially looked like a comet, but then didn't move the next night, he kept track of it because he didn't want to be fooled again. And over time, other astronomers also sent in observations and discoveries of fuzzy objects, and Messier eventually compiled all of these discoveries into the Messier catalogue. Okay, so there are 109 objects in the catalogue. There's actually one duplicate in there. Okay, so that it goes up to 110, but there's actually only 109 objects, and about 40 of them are galaxies. So if you're interested in looking for galaxies and you've got a go-to telescope, the majority of, well, not the majority, but certainly a big proportion of the objects are galaxies on there. So you can kind of like search through your handset on your go-to telescope and just pick them off one by one. Building on this, you've got astronomers like Dreyer, who were kind of like using discoveries by Caroline and William Herschel to come up with the new general catalogue. So you've probably seen NGC catalogue numbers in your astronomy books and magazines before. And as you dive deeper and deeper into the universe and find these fainter and fainter objects, a bigger proportion of them turn out to be galaxies. I mean, it makes sense when you think of it, because all of the kind of like distant stuff in the universe that we can see are galaxies. All of the nearby stuff belong to just one galaxy, our galaxy, the Milky Way. So you can't see star clusters and so on at great distances, but you can see galaxies. So when you look into the universe, most things are galaxies. So as you kind of like go from the 19th to the 20th century, you get these catalogues, which are just primarily galaxy catalogues. So the index catalogue is another one you'll find on your handset usually. So IC catalogue numbers. So these are mostly galaxies at this point, but there are so many more. As telescopes and astrophotography developed during the 20th centuries, astronomers just began recording fainter and further galaxies within their catalogues. So there you go. So there's a typical patch of the sky. This happens to show the galaxy cluster Abell 68. And you can see that the deep universe is just galaxies upon galaxies. Okay, so I'm going to kind of like make sense of that picture as we go through this evening. Now, I'm not going to bore you with this, but you must be aware that there are, we're getting on for billions, almost trillions of known galaxies in the universe. So not surprisingly, there are many, many galaxy catalogs. And many of these are accessible to kind of like astrophotographers with, 8 to 10 inch telescopes, they're going to look like kind of fuzzy blurs or even distant stars, but you can see them. You can actually track light, which has taken upwards of 1 billion years to cross space to your telescope. So they're all catalogued, and we're kind of mapping the universe by counting galaxies as well. Now, you probably have a good idea about what a galaxy is, but just over 100 years ago, we didn't, okay? The picture that you can see on the screen is a sketch by the 3rd Earl of Ross, William Parsons. That's his telescope on the right, nicknamed the Leviathan. It is a huge telescope, and he catalogued and drew several what were called spiral nebulae. So these are entries in Messier's catalogue, like M51 or M100. And he drew pictures of them. And the debate back then was, are these kind of like vortices, like swirling clouds of gas and dust in kind of like a larger Milky Way? Or is this a distant version of the Milky Way? Is this, if you could get up close to it, is this what we would term another Milky Way? So at the time they were called spiral nebula, but there was much debate about what they actually were. Now, last night was clear. I hope you were able to take advantage of that. One of the objects I went for last night was something to illustrate this kind of like difficulty in thinking about near and far objects in the universe. So this is a picture taken last night, and you can see the issue. I just pointed this towards NGC 6946. That's the spiral nebula at the bottom. Above it and all around it, in fact, you can see stars. The star cluster is NGC 6939. So, I mean, they look roughly the same size in the picture. So is the spiral nebula nearby the cluster of stars? I mean, are they kind of like just, a few light years apart? Or is the galaxy hugely, fantastically big, but very, very, very far away? If you've seen that episode of Father Ted, you'll get the idea behind this. So how do you resolve this? Well, astronomers needed to measure distances in the universe, so that's what they began to do. So in the early 20th century, there were two kind of like schools of thought on this. The Milky Way is the universe, okay? And those spiral nebulas are just part of the universe, which is the same as the Milky Way. Or you had another camp of astronomers. Where's the picture? No picture. Oh, that's a shame. The other school of thought was that you've got island universes. So that spiral nebula is a distant version of the Milky Way. The way it was resolved was by using what astronomers call standard candles. So I've talked about Henrietta Swan-Leavitt in the past, but she discovered a particular rule governing the behavior of a variable star called a Cepheid variable. Now, these stars were discovered a couple of 100 years ago, and they basically pulsate in brightness over periods of days or weeks or even months. And the longer the period of pulsation, the more powerful the star is. And, it's a very, very strong, tightly correlated law. It should be called like Swan-Leavitt's law. And I think there's a push for it to be named that. But it means that if you're looking at through a really big telescope, the Andromeda Galaxy, and you're able to resolve it into stars, you can measure the distance to it by looking for these particular variable stars. If you can measure a Cepheid variable in the Andromeda Galaxy, and it's got a period of months, then you know intrinsically how bright that star is. And you can say, well, because it looks that bright in the sky, but really we know it's like a really luminous, powerful star, we can gauge the distance to these galaxies like the Andromeda Galaxy. So these standard candles, as they're called, and there are many other types, work and they allow us to gauge distances across the universe. So Edwin Hubble applied this standard candle to the Andromeda Galaxy, and he discovered that the Andromeda Galaxy was at least 700,000 light years away. The modern estimate is 2.5 million light years. So this is definitely not part of the Milky Way. And if it's 2.5 million light years away, to be that big in the sky means it must be like 200,000 light years across. So you're able to start giving distances to the galaxies that we can see in the sky. So if you combine that with direction in the sky and distance, you can begin to map out your surrounding neighborhood. So this is a map of the neighborhood going out to about 10 million light years. So these distances to these galaxies in the picture were all gauged using Cepheid variable stars. So the Milky Way is plotted in the center. That's simply for convenience. We're not in the center of anything. And you can see the Andromeda Galaxy down at the kind of like center right there. You've got the Triangulum Galaxy in yellow as well. And there's a ragtag group of about 40 other galaxies in this group in the neighborhood as well. So collectively, these are the local group of galaxies. The majority of these are very, very small galaxies. Okay, if you've traveled to the southern hemisphere, you might have seen on a clear dark night the Magellanic Clouds, which look like detached parts of the Milky Way. They are in fact small galaxies, and many of the other galaxies in this picture are similar to the Magellanic Clouds. So really the Milky Way, the Andromeda Galaxy and the Triangulum Galaxy, those are the three big galaxies in this group. The rest are much, much smaller. And they're dominated by the gravity of those big three. So, my presentation isn't working properly tonight. Now, I've mentioned redshift and blue shift before, so I'm not really going to like go into this a great deal. But why are my pictures not showing up here? This is really annoying. I don't know what's going on. Is it like that all the way through? No. Okay. I'm going to have to draw it like old style teaching. Right, here we go. Here we go. So you know when you get a spectrum, right? A spectrum is basically like a rainbow of colors. My pen isn't working. At least I'm not recording this. Oh, I am recording this. Right. Okay, no problem. So a spectrum of colors kind of looks like that. So you might have like red over here, blue over here. And when you take the spectrum of a star or a galaxy, it's kind of crossed by particular lines. So you might have like a line there, a line here, a line here. And if you were doing kind of like a measurement of a galaxy moving away from you, okay, a galaxy moving away from you, it would look like this. You'd have a spectrum of light. This is still the red part of the spectrum. This is the blue part, but the lines get moved this way. So it goes to there, for example, and these two get shifted over to here. And the amount by which they get shifted depends on the relative speed between us and whatever the thing is that you're measuring. So if something was coming towards you, you might guess what's going to happen here. You got the red side and the blue side of the spectrum. Compared to this one, that line moves to here, and these two move this way. So if something's coming towards you, the light is blue shifted. So the amount of shift tells you about the relative speed between us and the object. And it turns out that for like most galaxies that we see in the night sky, their light is red shifted, which tells us that us and the galaxy are rushing away from each other. Okay. So Hubble didn't discover this, but he kind of investigated this for lots of galaxies. And because he was able to measure distances using the Cepheid variables, and he was able to measure the redshift and attribute that to a velocity of recession, he kind of came up with a graph which looked a bit like this. Okay. So on the one hand, you've got kind of I always forget which goes on which axis here. I'm going to put the speed here, so that's velocity, and the distance here. So when you kind of like plot like for a few galaxies going out in terms of distance, getting further and further away, you find that this galaxy looks like this one looks like this one looks like this is this is this, this is this, this is this. And you plot them and you keep plotting them. You find that there's a bit of a correlation, which you can kind of like draw a straight line through. So Hubble discovered that the further out into the universe you look, the faster galaxies appear to be receding from us, and it's called the Hubble recession. Okay, so galaxies are a kind of tracer of this recession built into the fabric of the universe. So one way to interpret this is that the universe itself is getting bigger, which means that all of the space between all of the galaxies is increasing as well. It's like new space is being created between all the galaxies in the universe, new space. So that's kind of like pushing them apart. Okay. So if those red circles represent galaxies, then at a later time, you get the picture on the right. So all the galaxies are moving away from each other, but no galaxy is kind of like at the center of the expansion. So I'll try and illustrate it with this picture. Okay, so imagine this is the Milky Way in the middle. Okay, so what we see is we look out in every direction and every galaxy is moving away from us. Okay, so this galaxy here appears to have a small velocity. This galaxy a bit further away appears to have like a bigger velocity. If you look in the other direction, the pattern is repeated. In the picture, it looks like we are the center of the universe and everything's rushing away from us. But if you imagine yourself being in one of those other galaxies, so for example, that galaxy there, when they look into their universe, into their sky, they see exactly the same picture. So they see us rushing away from them at some great velocity. So every galaxy in the universe has the same view. There is no center to the universe. Okay, so interpreting this as us being at the center is just plain wrong. So it's the same wherever you go. Now, galaxies are the tracers of this expansion. Without galaxies, without all of those faint fuzzy blurs in the night sky, I don't know how we'd figure out that the universe was expanding. I don't think we'd be in the 21st century talking about the expanding universe. There's likely other ways you can do it, probably using like the cosmic microwave background. But the reason that was looked for at all was to look for evidence of the expanding universe. And it was an accidental discovery in the 1960s. So we might not even know about the expansion of the universe if galaxies weren't out there moving away from us. Now, Hubble didn't really involve himself in cosmology discussions. What he got back to after he kind of made these discoveries about the Andromeda Galaxy and the recession of galaxies was about finding out what galaxies were and classifying them. So he had a huge sample of photographs to look at, and he sorted through them, and he basically sorted out these different types of galaxy. And this is a diagram taken from one of Hubble's books in the 1930s about the subject, and it's popularly known as the tuning fork. So Hubble believed this to be an evolutionary sequence. He thought that galaxies must start out round, and then perhaps because they're rotating, they flatten out into a disk, and then over time, those spiral arms emerge, and then eventually those spiral arms might destroy themselves, and you end up with it's not in the picture, but there's a kind of another shape of galaxy called the irregular galaxy. So these spiral galaxies kind of collapse and become these kind of irregular shapes as well. So he believed with time passing that galaxies evolved like this, and it branches out into two. You've got normal spirals and you've got these galaxies which have bars in the center of them. Okay, so I'm going to show you some photographs to kind of back this up, but the short story behind this is that Hubble was pretty much wrong about what was going on here, but it influenced astrophysics well into the 20th century, and to this day astronomers call these early galaxies. Okay, and we call these late galaxies. Whoop, can't spell it. So even though it's no longer, proper terminology in the literature, you still find these terms describing galaxies. It's very misleading. As I've said before, astronomers are very resistant to change. Now, elliptical galaxies look like this. These are the dullest things, I guess, to look at through the eyepiece of a telescope. They're almost completely featureless unless you've got access to astrophotography or the Hubble Space Telescope. So they tend to be featureless. They're bright in the middle. They tail off in brightness as you go to the extremities of them. And they vary in shape. So for Hubble, you've got like E0 galaxies. You've got E1, E2, E3, all the way up to like E7. The number is a measure of how elliptical it is. And there is a mathematical way to calculate that. Elliptical galaxies are smooth and featureless. They don't have spiral arms. They don't have like dust clouds within them. About 20% of galaxies are elliptical. There's a list of subtypes. You've got normal ellipticals, like the one you were just looking at before. You've got centrally dominant ones. That means when you get like a big cluster of galaxies, quite often the one in the middle is a really, really big elliptical galaxy. And all the others, to some extent, have their motion through space dominated by it. Perhaps they orbit around it. And beyond that, you've got dwarf ellipticals and dwarf spheroidals. Okay, I guess the most famous example of a dwarf galaxy would be the two companions that you see in pictures of the Andromeda Galaxy. So those are dwarf elliptical galaxies. The E number is, you can calculate it. You basically take your galaxy and you measure the long axis, which is A, and you measure the short axis, which is B, and you plug them into that formula there, and it gives you a number which you can round up to the nearest like integer. So that's how you kind of measure it. So yeah, that's how Hubble did it. He measured dimensions and came up with like these kind of like systems up here for E0 to E7. Now, after that, you get kind of like where it branches, you get your lenticular galaxies. So Hubble thought these were basically spirals which hadn't yet developed arms. And this is an example of a lenticular galaxy in the picture. You might recognize it. I think this is M104, possibly, as taken by the Hubble Space Telescope. So Hubble believed this to be a transition between the ellipticals and the spirals. Quite often, these have lots of prominent dust lanes along them, that spirals do, but they don't have the spiral arms. Now, spiral galaxies then branch into the two kind of like features along here. So you've got a class which has a bar in the center. So those are your SB classifications along here. So like SB, SBB, SBC, and so on. And they've got features which are common to them. So you've got like a central bulge, but the bulge is kind of like becoming less important. So here's a big bulge here. Here's a small bulge in that one. The disk becomes more important. The spiral arms become open and more ragged. And the barred spiral is the same, except for there's a bar in the middle of it. Now there's the Andromeda Galaxy. And these are the two companions, which are the dwarf ellipticals, which I was mentioning. But Andromeda Galaxy itself is a spiral galaxy. Now, this picture should show you a problem that astronomers have as well. Galaxies can be oriented in any direction in space. So if you're looking at a galaxy like the Andromeda Galaxy, it can be difficult because it's almost edgeways on to figure out what kind of spiral it is. And to measure things about it in any kind of like meaningful way. This is an example of a spiral galaxy which is presented face on. This is the galaxy M101, which is a target usually for the late winter, I think. It's in Ursa Major. And you can see these beautiful spiral arms within it, and we're looking like either down from below or, you know, from above, whichever way you want to think of it, down on the galaxy. So Hubble was able to classify all of these, and he believed that these were kind of like an evolutionary sequence. Now, what we think happens is actually very different. So we don't think elliptical galaxies form first and spiral galaxies come later. And we certainly have a different idea about what causes the spiral arms in a galaxy. Now, the analogy to what a spiral arm is a traffic jam on the A1, effectively. Okay, so if you've driven kind of like, you know, past Newcastle in rush hour, you know, like on the Western Bypass, you're quite often in stop-start traffic, and it's almost like when you're stopped, that's the spiral arm of a galaxy. It's kind of like you are a star, and the jam that you're currently in is a spiral arm, and you move through the arm, okay, and you start moving again, and the jam itself kind of like backtracks through the traffic on the A1. The jam is not like a physical thing, is it? It's just comprised of different cars at different times. And a spiral arm is kind of like that. A spiral arm is not a physical thing that exists. A spiral arm at any given time is just constituted of stars which happen to be moving through a region where the gas was a bit denser, and therefore more stars were able to form at that point. But the stars themselves are orbiting around the center of the galaxy, so they move through there, and eventually they cross another spiral arm, a place where the gas was more dense and more stars happen to have formed there as they were passing through it. So it's a very difficult thing to visualize. Oh, I'm really glad this video appeared there. This is a picture of a spiral density wave. Now, just take a look at it for like a moment or two. I don't know how smoothly this is showing on your screen, which is kind of the worrying thing for me. But try to keep track of like the stars that are appearing near the spiral arms. You can see that the stars don't stay in the spiral arms. They kind of like move out. And because galaxies take hundreds of millions of years to rotate, and the stars that you're seeing appear, then disappear, they're typically high mass stars which live for a few million years and then explode and disappear because they become supernovas. So the stars, what you're seeing is gas clouds compressing, which creates the bright stars that you see forming the spiral arm. But those stars are moving and they live for a few million years and then blink out. And then the gas compresses again a bit further on as it crashes into other gas and dust clouds, and new stars form there. So it's like a traffic jam with cars. It's kind of like the spiral arm is not a physical thing that you can kind of like take apart, and it's always the same. It's comprised of different stars at different times, and these things persist because of that. If spiral arms were just made of the same stars and they wound up like that, they'd wind up so tight that the arms would just break apart, and you'd have featureless galaxies within a billion years, I think. This is a really lovely picture showing all of that gas and dust compressing. So if you look along the spiral arms here, you can kind of get an illustration of what's going on inside the galaxy. You can see these bright red nebulas, which are the stellar nurseries. These are places where gas clouds have compressed and crashed into other gas clouds. They have heated up, they have sparked star formation. Okay, so the new stars appear here. Perhaps that's one, perhaps that's a cluster of stars there. And on the kind of side here, so the rotation is going this way, those gas clouds contain dust particles, and as they compress and push together, the dust becomes more dense, and you can see it. So on the kind of like trailing side of the galaxy, you get these very dense dust clouds, which lead to star formation, which lead to all of these new stars, which you can see in the form of those blue star clusters there. And the whole thing is rotating gracefully over periods of hundreds of millions of years. So that's our kind of like modern picture of what a spiral galaxy is. I'm just checking the chat. Why do the galaxies appear to rotate? Do they? You might have to elaborate on that a little bit at the end of the talk. I guess maybe it's. Are you suggesting it's because it looks like a vortex kind of thing? It looks like water going down a plug hole. We do know that galaxies rotate because when you take the spectrum of one side of a galaxy and the spectrum of another side of a galaxy, particularly if it's an edge-on galaxy, one side is coming towards us and the other side is going away from us, therefore rotation. Okay? We'll come back to that if need be. Barred spiral galaxies look like this. So you can see in the core of a barred spiral galaxy, there's a kind of linear feature through the center. So these galaxies rotate as well. The origin of the bar is not fully understood, least of all by me, but about half of all galaxies have a bar structure, including the Milky Way. And they're kind of what happens when the orbits of the individual stars influence each other, we think. It's like you've got billions and billions of stars orbiting around the center of the galaxy, and you kind of get correlation between the orbits. So again, the bar isn't like the same thing all of the time. It's made of different stars and different orbits, but the bar itself does rotate. So it does kind of like rotate with the rest of the spiral galaxy. Dwarf galaxies. This is an example of one. It's the Large Magellanic Cloud, which looks like a detached part of the Milky Way, if you've ever seen it. So where the Milky Way contains maybe 100 billion stars, these might contain 1 million or 100 million or even less. So they're very, very small galaxies. They're very low surface brightness. And many of these kinds of galaxies weren't discovered until astronomers began putting cameras onto big telescopes in the 20th century. So, for example, the Milky Way has dwarf galaxies orbiting around it and, in fact, being cannibalized by it as they crash into it. And they weren't discovered until like the 1970s and 80s in some cases. Here is a couple of examples. So these are two dwarf galaxy companions of the Andromeda Galaxy. So you've got NGC 205, which is a dwarf elliptical, and NGC 147, which is a dwarf spheroidal. Look at how faint it is compared to the background sky. All of the stars in that picture are stars in our galaxy. This faint smudge of light, you can't see any of the individual stars within that galaxy. It's just a diffuse elliptical glow against the sky. Now, after your ellipticals, your lenticulars, and your spirals, you've got the irregulars, okay? We know these now to be interacting, merging galaxies, but at the time, like 100 years ago, these were just classed as irregulars. I think Hubble thought that this is what all galaxies kind of like break down into. They fall apart and form these weird and wonderful shapes that you see. So there are lots of these scattered across the sky. This is the mice galaxies. And astronomers wanted to figure out how you can form these shapes, perhaps by blending other types of galaxies together. So it's a very difficult thing to calculate. So we know, like, Isaac Newton came up with a theory of gravity a few hundred years ago, and his theory is beautifully simple, okay? If you've got two masses, one mass and another mass, they attract each other, okay? There's a force of attraction between them, which depends on their separation and the size of the two particles. And the equation is simple. I mean, you might look at that and think it's not simple at all, but that's a simple equation. You can solve it. If you know the mass of two things, you can figure out the force between them and therefore how they move for all time. However, galaxies, as you know, are made of hundreds of billions of stars. So how do you figure out what a galaxy does if another galaxy passes it? Well, you've got to try and figure out how all of those hundreds of millions of things affect this other group of hundreds of millions of things. And you plainly can't do that. And in fact, Newton's equations cannot be solved if you've even got three masses, okay? So it's a very, very difficult thing to do. So we'll settle on having a rough idea of the answer, but even that means you need fantastic computing power. Now, this is a picture from a paper, and you can see that you've got a galaxy here interacting with another galaxy, but this galaxy is made up of like 50 dots, okay? And it's interacting with another galaxy which has like 50 dots as well. And that's, if you have any more than that, you can't do it on paper or even with a computer back, like 50 years ago. So astronomers were trying to extrapolate using very limited computing power how you might produce those shapes. And it was a very, very difficult thing to do until the advent of modern, powerful supercomputers. But it did look like you could interact spiral galaxies or other types of galaxies together to produce these weird and wonderful tails and things that you see in the night sky. I'm hoping you can see this movie when I play it, but these kind of illustrate how a couple of spiral galaxies interacting and the laws of physics as set out by Isaac Newton can produce these weird and wonderful shapes that you see in the night sky. So the galaxies approach each other, and if you plot the trajectories of all these masses acting under the influence of all the other masses in the other galaxy, it does match many of the examples of the weird and wonderful objects that we do see in the night sky. So these are simulations being compared to actual observations. So it's pretty convincing when you see it like that, that's what's going on, that those strange shaped galaxies were actually the results of mergers of other kinds of galaxies. And it means that Hubble was definitely wrong when he thought that all galaxies end up being like this as a final result, because they don't start out as ellipticals a lot of the time. At the end of this process, quite often what you're left with is a big blob, an amorphous blob of stars, which are the ellipticals. It looks like the ellipticals are actually the last ones to form, and the spiral galaxies are certainly around before that. The other thing with Hubble's classification system of, looking for shapes is that it's very kind of like based on what we see with our eyes, okay? We've now got telescopes capable of looking at infrared, radio waves, gamma rays, ultraviolet, and galaxies look very different depending on the type of wavelength you look at it with. So, for example, a spiral galaxy might look like that when you view it in gamma rays. So the shape is just not there at all. And it's true for other galaxies as well. For ellipticals, sometimes we get intriguing suggestions that they might not be as quiescent as we think they are. Anyway, astronomers really haven't given up on this system. So you still see papers referring to kind of like early and late, E, S, and so on. And there are trends as you go across Hubble sequence. So for example, the ellipticals tend to be made of stars within them. Okay, so there's an elliptical galaxy, and the stars, the reason they have that shape is because the stars kind of like have orbits around the center of mass, which are oriented in random directions like that. Okay, so stars go around them randomly, and there's hundreds of billions of them. So at any given time, you're going to have stars out here and stars over here and stars over here. And astronomers call that like pressure support. In spiral galaxies, you tend to have stars orbiting in concentric orbits like this. So they tend to be disc-shaped and flat. So as you go along the sequence, there's a change from this random orientation to this flat orientation. Ellipticals tend to be red, spirals tend to be blue. That means the stars in ellipticals tend to be old and red and yellow, and the stars in spiral galaxies tend to be blue and hot and young. And there are other correlations as well. So that's why probably Hubble's kind of system of naming galaxies has hung on for so long. So when we look at this, we see that elliptical galaxies have lots of old stars, and we think that they had a big burst of star formation near the start and very little goes on now, whereas in a spiral galaxy, you don't have as much star formation, but it's prolonged throughout the life of the galaxy. So that's what you have. That's what you see as you go along Hubble sequence as well. Now, I just want to kind of like give you a picture of what we use kind of all this information for. I say we, I mean like modern cosmologists. So we're using galaxies to map out the universe because galaxies influence each other, and they also are influenced by the stuff we can't see, so-called dark matter, which seems to be out there. So galaxies tend to clump into groups called clusters. So the local group is our kind of small cluster, but the local group is part of a much bigger aggregation of galaxies as well. So you've got to figure out the shape of the landscape around us by looking at different distances to galaxies. So here's a kind of map to give you an idea of what the large scale universe looks like. So if you plot the positions of galaxies on the sky, there's a kind of region around here called the zone of avoidance, and that's basically in this map, that's where the Milky Way would be, and you can't easily see past the Milky Way to see what's behind it. But in the rest of the sky, you see galaxies in every direction, but it's not completely random, is there? I mean, you kind of look here and you see this really big, long feature here, and you see kind of like other kind of structures here. You see this huge group over here. Galaxies tend to be arranged into big groups called superclusters, and we began discovering that in the 20th century. So they've got names. We've got the Perseus-Pisces cluster, the Hercules. We've got the very famous one, which every amateur astronomer goes for in the spring, which is the Virgo cluster, that one there. And the rest of the universe seems to be organized into galaxy clusters like that. Now, our local supercluster was discovered by mapping these things out. So the first modern kind of like measurements of the supercluster that we reside in were made in the 1980s. So the supercluster we belong to is the Virgo cluster. And the local group is kind of like a tiny outpost of that near the outer edge. So this cluster is about 150 million light years across, something like that. This is a bigger map. You can see the local group that I showed you before in the center. So the Milky Way and us, we're still in the middle of this picture. And here is the Virgo cluster. So we're kind of like an outpost. And not surprisingly, because this is a big mass of galaxies, the local group is strongly drawn towards the Virgo cluster. We're actually approaching that at quite some speed. So yes, the Andromeda galaxy is coming towards us, we're moving towards it, but in the long term, we're all heading towards the Virgo cluster, which is about 50 million light years away. Clusters are classified. So modern astronomy looks at these clusters, and some of them have got these giant ellipticals in the center. So these are the centrally dominated ellipticals. Others don't have them, but you know, astronomers are looking and classifying all the time. I'm just going to show you kind of like different maps of the universe here. One of the things that I found interesting was how astronomers measure redshifts of so many galaxies. I mean, we're talking hundreds of thousands, millions of galaxies now, and we measure the redshift. So the technique is you take a picture of the bit of sky you want to analyze, which might contain like 500 galaxies. From the picture, you place an instrument at every point in the picture where you know the light of a galaxy is going to fall. And that instrument will take the spectrum of that individual galaxy. And from the spectrum, you can figure out the distance to the galaxy in most cases. So using this kind of technique, you can keep track of hundreds of galaxies in a single picture. And I thought it was quite interesting to see how they did it. So when you build up a map of the universe, it looks like this. And again, we are at the center. But again, just remind yourself, it doesn't mean we're at the center of the universe, but we're at the center of the things we can see. And as you look out in different directions, you kind of you get a picture of how kind of like fractured the universe is when you look at galaxies. So there are big walls of galaxies, but there are also like huge voids in between them. So there are places in the universe measuring tens of millions of light years across where there are virtually no galaxies at all. Okay, so in between the clusters, there are giant empty voids as well. You might guess that that's just because gravity tends to pull things together. So they're quite naturally going to pull things away from other areas, I guess. You can also look into the universe. You can do what we call a pencil survey. So if you just like look at a tiny, tiny, minuscule region of the night sky and just measure through that volume of space, you kind of see the walls in there as well. So you see there are structures here. There are big walls of galaxies here, and you see something here. But in between, you've got regions where there are big gaps as well. So we're building up kind of like three-dimensional views of the universe out to distances of billions of light years. So this is a real big picture of the universe and the galaxies, and we see the superclusters in here. So the Virgo cluster is part of the Virgo supercluster. You've also got these other clusters of galaxies, and it's easier to see the voids in this picture as well. Again, just more pictures, more surveys, but you get the impression that we're looking at vast swathes of the universe when we do this. We're really figuring out how stuff works. And the reason things look like they peter off in the distance is not because of any real kind of disappearance of material. It's simply because it gets harder and harder to see that far into the universe. So we can see more clearly the things that are nearer to us. And beyond a certain point, we need bigger and bigger telescopes to carry out the job. So the James Webb Space Telescope will be better than Hubble if it ever gets launched. It's seeing these distant reaches of the universe. Again, we're looking at now surveys which are taking in billions and billions of galaxies. This is probably one of the most famous pictures of recent years, and it's the Hubble Ultra Deep Field image. So this is a piece of sky about the size of a pinhead held at arm's length in a kind of empty part of the sky, and it's just filled with galaxies. So in this picture, some of the bigger blobs are galaxies which are nearly 1 billion light years away. Some of the tiny dots that you see in there are getting on for 13 billion light years away, or certainly that's the time that light has been traveling from them. The actual distance is probably 40 billion light years at this point, because the universe has expanded and the time that the light has been traveling towards us. So we're getting very good at classifying galaxies. So I want to show you one more video. This is a simulation of all of that data of how the universe looks when you're looking at galaxies. So you really get the impression that there are big superclusters that we've just flown through, but there are immense gaps and bubbles and voids between them as well. So this is a simulation, but every galaxy in that picture is a real galaxy. It's extracted from an image and put into the simulation at the appropriate distance. So that's the universe on the biggest scales imaginable. I mean, it ties into, there are 100 billion stars in a typical galaxy. And we don't know of life anywhere beyond the Earth. But looking at a video like that, it becomes quite difficult to argue against there being life, at least in one other place in amongst all of that. Anyway, there you go. That's the universe. Now, the reason surveys like this are important is because galaxy clusters themselves move, and we can track their movement through the universe. So within a particular group of galaxies, the galaxies might be moving towards each other or away from each other. They're kind of like being pulled around by each other, but the cluster itself might be moving through the universe in a completely different direction. We can do this with nearby clusters. We can map out the velocity field, as it's called, of all the galaxies in the neighborhood. And what we find is for our galaxy group, the local group here, so that's us, the Andromeda Galaxy and all that other group of galaxies, part of our velocity, as I said a little bit earlier, is being directed towards the Virgo cluster. So we're being pulled towards the Virgo cluster by gravity at 220 kilometers per second. Okay, all of our group. But the incredible thing that we discovered was that is actually not where we're really headed to. There's a big component of our motion in a completely different direction. And we're being dragged towards a structure which is absolutely immense called the Great Attractor. You might have heard of it or you might not have heard of it, but this is an immense wall of galaxies, billions of light years away from us, containing millions of galaxies with a combined mass which dwarfs the Virgo cluster. So by studying the kind of the movement of the clusters, we're able to figure out a lot about where we're actually headed to. So the Great Attractor is annoyingly hidden by the Milky Way. Okay, so we don't have a great view of it, but here it is. It's this big in the sky. So if you think about that in the night sky, that would fill like most of like the eastern sky, for example. If it was rising in the east, it would fill most of the sky. But it's so far away that you need powerful telescopes to be able to see the thing. And you certainly need to be able to see through the Milky Way to get that. So we're being dragged towards that. Another recent discovery by tracing the flows of all of these clusters is that we live in a much bigger structure than the Virgo cluster. The Virgo supercluster is part of something which has been named Laniakea. In the picture, the bits which are highlighted in yellow represent Laniakea. So this structure is like 500 million light years long, and it contains 100,000 galaxies. So really, this is kind of like after your postcode on your address. You know, I used to do this when I was little. I'm not ashamed to say. You know, when you write your address down and you don't stop at your postcode and you put like UK, Europe, not any longer, the world, the Milky Way, and then the Milky Way would be the Virgo cluster. Well, this is now Laniakea. That's the kind of last line on your address at the moment. So it's an immense structure, and we've been able to figure it out using the motion of all of these other clusters. It's a very difficult thing to do, but there we go. So that's a picture of where we are. Can you see where we are in there? There's the local group over here. Okay, so you've got all of these other groups as well. I'm nearly done. Like I said, computing how galaxy and galaxy clusters move is not something which was easy to do. I thought one of the interesting ways they did it initially was to use light bulbs because light follows the same pattern of fall off as gravity does. If you move twice as far away from a light bulb, then the brightness of the light bulb falls to a quarter. The gravity, if you move away from something, falls to a quarter as well. So if you set up lots of light bulbs and then you kind of like move them and then see how bright every other light bulb looks from it, that's kind of like modeling gravity using light bulbs. So they did this in the 1940s and figured out how interactions of galaxies could kind of like tell us about the universe. So then we have computer simulations into the 60s and 70s, and then we just have better and better computers. And the reason all of this is important is because the shapes that we predict depend on what we think the universe is made of. So if you kind of like look at the universe and you see, well, we have lots of superclusters and lots of big voids, the only way you can get that recipe looking right for the real universe is to know something about what the computer does about dark energy. So you've got to feed in the right ingredients into the computer. So if you've got an idea that the universe is filled with dark energy, but not dark matter, and then you run the equations, the universe it predicts doesn't look like our universe. And in fact, that's why we think the universe is permeated by this stuff called dark energy, which is a bit like anti-gravity. It's because the predictions fed into the computer and the output matches what we see in the night sky with the real galaxies. So studying galaxies really does tell us about the origin and evolution of the entire universe. Without galaxies, we'd be lost in understanding the universe as a whole. Right, the last thing I'll mention is that Hubble got it totally wrong. How we think galaxies are made is by small pieces bonding together to make big pieces. And you kind of get a hierarchy which looks like this. So the dwarf ellipticals and the dwarf galaxies are kind of like the asteroids and the comets of the solar system. They're pristine examples of material from the early universe. So if we can study dwarf galaxies in more detail, we'll understand more about how the rest of the galaxies actually formed themselves, because they're kind of like preserved record of the early universe. So small dwarf galaxies form to make big galaxies. You get spiral galaxies built after that. There's always some kind of rotation within them. Spiral galaxies interact, their shapes become disrupted, and the whole thing's collapsed down to giant elliptical galaxies in the end. So that's what's going to happen to the Andromeda Galaxy and the Milky Way eventually. 7-8 billion years down the line, there won't be two separate beautiful spiral galaxies. There'll be one gigantic amorphous elliptical. Right, okay, so that's it. So just to really summarize, galaxies are the building blocks of mass in the universe, okay? They're just a small component of the total mass. We think dark matter forms a big component of most galaxies. Early classification schemes were hit and miss in terms of galaxy properties, but astronomers are really reluctant to drop the terminology, so you quite often see references to early and late in the literature. Mapping galaxies tells us about the universe. If there's one thing you take away from this, it's not that, galaxies are beautiful things to look at in pictures, and they're great things to track down in the telescope. but they really tell us about the universe. They're the things that tell us that the universe is expanding. And understanding them is one of the key kind of like goals of modern astrophysics. So there we go. I'm going to finish there, and I'll see if we've got any questions about that. Thank you.